Sir, now please try. Okay. Good morning, sir. Now you are in the meeting, sir. Sir, please unmute yourself.
Okay. Can you hear me?
Yeah, clearly, sir, clearly.
Okay. So we have, what is this join audio for?
Join audio, sir. You have joined the audio.
Okay.
Okay.
Because it's showing a button where join audio is mentioned, and then share screen. Share screen is possibly the way
Share
we.
screen for sharing your screen like
Yeah,
PPTs.
yeah.
So you can on your video also if you want.
Yeah. Is it necessary to do the full screen, or is it okay if I just go to the specific window?
So as per your convenience, I think you have to slideshow PPT only, no?
Yeah.
So you can go by window only.
Okay, by the specific
Otherwise,
window.
full screen. Yeah. Otherwise, full screen is very easy process.
Okay.
Sometimes there will be problem in window.
Okay. So, okay, usually we do full screen because sometimes the cursor doesn't match the objects in the presentation. I don't know whether it happens with Zoom
Yeah.
or
So please do. Yeah, please do full screen only.
okay. So, are you able to see my screen?
Yeah, sir. You have opened Zoom on your screen?
Yeah. So,
Yes.
I'll just check whether the presentation is coming okay.
Yeah, coming, sir, coming.
So, you can see the full, can you see the full
Yes,
slide?
sir. It is a yes, sir. It is in now slideshow mode.
Yeah, I'll just check whether animation is working. Just 1 second.
Okay, sir.
Is it coming okay?
Yes, fine.
Okay, I think we are set, so there should not be any difficulty.
Okay.
Uh, what should I do to? So, what is the sequence actually? I have to start at 10 o'clock. You will give me some indication that I have to start.
So I will give you a WhatsApp message at this number. Is it okay?
That's okay. That's okay. But I will not
We
be.
will.
I will not. Will I be knowing whether the people are? I mean, will they? Will it be possible to interact, or it will be just one way?
So as per your convenience, if you allow, we will give access to interrupt the person participants. Otherwise,
Yeah,
we will have a QA session in the last 15 minutes.
yeah, that's also okay. That's also okay.
Uh, I think in this platform, uh, keeping the QA session in the last 15 minutes is okay because interruption in the middle of the lecture will cause difficulty. I think.
Yeah, it's okay. I mean, whatever. If the participants want to interrupt me, I don't have any difficulty with that.
Okay,
Uh,
okay.
yeah.
So we
So
we
either
will.
way, it is okay.
Okay, sir. Okay, as per your convenience, sir.
Yeah, yeah. So now,
Okay.
what should I do now? Should I wait on this or should I just come out of this?
So I think you have to you will keep running on this and mute your mic and you should
Oh,
join at 10 a.m.
yeah. So muting the mic also is available on this itself, isn't it?
Yes, 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 yes.
Yeah, on the
So
mute. So this is the button which I have to press for mute my audio, right?
uh, I am not seeing your mouse cursor, sir.
Are you able to see? Are you able to see the
Yes, yes. Now your
mute?
mouse is visible, but
Yeah.
you are not on the same page. Please go on the first web. Yes, click on that.
Hello.
Yes, yes. You have been muted, sir.
Yeah. So I had when I had pressed it, it got muted.
Okay, 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 okay.
Okay.
So please,
So I just
uh,
have I can stop sharing now, and only when the session starts, I'll start the sharing, right?
okay, sir. Okay, okay. So please just start at 10 a.m., sir.
Okay, fine, fine, fine.
Oh, okay, okay. Thank you, sir.
Okay, okay. Welcome, welcome.
Good morning, sir.
Yeah, good morning.
Sir, I am Dr. Sandhya Dikshit, the session coordinator for this session. Please welcome to the program.
Okay. Good morning, madam.
Good morning, sir.
We'll be starting in another 10 minutes.
Sure, sir. Actually, let the participants also join. It's
Okay,
scheduled
fine.
for 10 o'clock.
Okay.
So you are the co-host now. So if you want to share the screen, you may.
Good morning, ma'am. I think we should start now.
That's what I was also thinking. Approximately 20 participants are there.
Yes, ma'am.
Anand sir, may we start?
Yes, we can start.
Okay.
So,
Okay. Okay, sir. Uh, Good morning and a warm welcome to all in the 12th session of this short-term training program on advances in manufacturing technology, CNC and robotics. Today, we have amongst us Professor Joseph Anand as expert speaker. Dr. Anand received his Bachelor of Engineering degree in Mechanical Engineering from the College of Engineering, Pune, University of Pune in 1985. MTech and PhD from the Department of Mechanical Engineering, IIT Kharagpur. He is presently working as a professor in the Department of Mechanical Engineering at B.R. Ambedkar National Institute of Technology, Jalandhar. Before this, he was a professor at Sant Longowal Institute of Engineering and Technology, India. He had also served with the Machine Tools Division of Messrs. Voltas Limited, India, and with Messrs. Shriram Diesels, Balanagar, Hyderabad. He has been an invited professor to LAIL, France. He was awarded a JSPS postdoctoral fellowship for foreign researchers in Japan and pursued research at the Department of Robotics, Ritusumiken University, Japan. He has been to the United States, France, Japan, Spain, UK, Israel, Italy, and Malaysia for dissemination of research work. He has completed a number of sponsored research and consultancy projects and is currently supervising 6 PhD scholars. He has coordinated and organized several MHRD and AICT sponsored FDPs on mechatronics, modeling and simulation, etc., and 2 GIAN courses. His research interests are in system dynamics and control, especially using bond graph mechatronics, robotics and automation, mechanisms and machines, simulation, understanding musculoskeletal actuation, and systematic development of prosthetic devices for rehabilitation of hand impairment. He is also very passionate about teaching and has designed many innovative lecture presentations with MATLAB-based simulations and developed several innovative experimental setups for mechatronics lab. Welcome to this program, Dr. Joseph Anand.
Yeah, thank you. Thank you very much,
Sir?
madam. Yeah, yes, madam. Can you hear me?
Yes, sir. You are clearly audible.
Yeah. Should I put on the video or I can just start?
Sir, as you wish. As you wish.
Okay. Yeah. So I'm starting my presentation. I think I'll need to put on the, I'll have to share the screen. Can all of you see the screen?
Yes, sir. It's visible.
Okay. I would like to, is there some way I can minimize this on the right side? Otherwise it may keep on blocking the presentation.
Sir, I think it's the icons on the top.
Yeah.
The square, the small square, the rectangular shaped icon. If you press that, I think it will be minimized.
Which one? This remote control?
No, sir. On your right side, all the participants must be coming. If you click, if you click on the top icon, it's a rectangular shaped icon.
Okay, okay. Yeah. Thank you very much. Thank you.
Now only the speaker will be visible if the single bar is activated. So only this.
That's right. Okay. So I'm going ahead with my presentation. So good morning to all of you. I would like to, at the outset, thank the organizers of this short-term program for providing me with the opportunity of sharing ideas and sharing discussions related to our work on modeling and simulation of robot dynamics using the powerful approach of bond graph. And my presentation will focus mainly on the research that is in progress at the mechatronics lab at the Dr. B.R. Ambedkar National Institute of Technology, Jalandhar. There seems to be some scratching coming up here.
Vimlesh, please stop the participants annotation. Vimlesh, can you hear me? Vimlesh, are you there?
I am here.
हाँ, please annotation stop करवा दो, कर दो participants annotation.
Yes.
Okay. So the outline of my presentation will include applications of robotics in manufacturing technology. I'm not going to dwell on this aspect much because if you open the YouTube and give a search on robotics in manufacturing, you will get hundreds of videos giving you wonderful insights into the applications of robotics in manufacturing technology today. And that's perhaps not where the real challenges lie. That's the reason why I thought that I'll rather focus on a very brief discussion on the fundamentals of the bond graph method. Of course, we will not be able to go much in detail, and also how it can be used for robotics, for the modeling of robotic systems. So we will discuss bond graph applied to robotics. The modeling of dynamics of robotic applications, we'll see a number of these in our presentation. And there are several challenges. So we'll discuss as we discuss each application, we will also discuss the challenges associated with each of these. And each one is a case study which we have done at the mechatronics lab at NIT Jalandhar. Finally, we'll conclude. So coming to the topics that we will discuss, I'll provide a very brief introduction of bond graph and the essential features why we use this technique. Now, bond graph, you must have heard, many people who deal with mechatronics must have heard that it is one of the good approaches to model physical systems, especially mechatronic systems. Bond graph is a graphical approach. It is used to model the dynamics of physical systems. And graphical systems are easy to understand rather than pure mathematical approaches. Bond graph is a unified approach suitable for modeling dynamics of multi-energy domains. So you can handle systems in the mechanical engineering domain, in the electrical domain, in the thermal domain, in fluid domain, in the chemical domain, or you can also, you can have a mix of these like electromechanical systems, electromagnetic systems. So bond graph offers you a unified approach suitable for modeling dynamics of multi-energy domains. Now, first of all, why is this modeling essential at all? Why are models needed? There are several reasons. Prime among these are, first of all, you would like to study and understand the behavior or the response of a system when it is subject to various conditions. For that, you need a model. You would like to perform experiments or simulations and make measurements. For that, again, you need a model. You require a model for design and testing. For control of physical systems, this is a very important objective in engineering. For this also you need models. Models are also helpful for derivation of system equations and computer coding, which is necessary for simulating these models. Modeling of physical systems is therefore an essential requirement for studying the response of physical systems. Now, there are several ways in which you can do modeling. One of these methods is a graphical method. Now, what about these graphical methods? Are pictures and graphs easier to understand than equations? I'm sure all the participants will agree with me that if things are represented graphically, we will be able to understand mathematics better. Can mathematical features of dynamics be represented pictorially? So if we have a model which is in the form of which is a graphical model, it should represent the mathematics of the system as well. Now, can the mathematical features be represented in the pictorial form? Can graphical modeling methodology be applied to any energy domain? Can we apply it to electrical, mechanical, magnetic, thermal, any domain? Can system equations be derived easily from a pictorial model? How do we simulate this model of a dynamic system in a simple, easy manner? Can simulation code be derived automatically from such a model? Can a pictorial model offer insight into analysis for design and control? So you have several questions in your mind. And bond graph offers you one solution as a unified approach to the modeling of physical system dynamics. You can certainly apply it also to robotic systems. Now here is a electromechanical system. Actually, there is also a magnetic system in between, but let's just restrict it to an electromechanical system. So you have the electrical part, which you can see here. You have the resistance, the inductance, and this is on account of the armature winding. You have the permanent, you have the brushes, you have the permanent magnetic field. You have also the mechanical side where I hope you can see the cursor. I'll use a laser pointer. So you also have a mechanical side which is going to rotate the moment you apply potential difference across this. So this is an electromechanical system. You can model this using bond graph like this. Now here you must be wondering, what is this? You have some letters and you have some arrows, half arrows. Well, actually this is just indicating how the flow of power is taking place. So here you have the input, electrical input from here being put into the system. There is a one junction here, and part of it is going is getting dissipated through this resistance. Part of it is going to this inductance. It's an energy storage device, and a part of this power goes into conversion into the mechanical domain. So from the electrical domain to the mechanical domain. So the current gets reflected as torque on the mechanical side. It gets translated to torque on the mechanical side, and that is responsible for changing the angular momentum of this rotor. And you may also have a bearing resistance here, so which is shown over here. Now in this picture, you can just see how the flow of power has been depicted. You have made use of certain elements. Now, if we see, we have made use of elements and we have made use of certain grammar which is of a pictorial nature. So here, before we proceed further, I would just like to give a brief introduction. The idea of bond graph was presented by Professor Henry Painter sometime in the 50s, 1959, when he made his first presentation on this. He's credited as the inventor of bond graph. And this is a picture which I have taken from the MIT website, where he worked as a professor for several years. And he developed the pictorial grammar for the modeling of physical system dynamics. Essentially, it consists of the power bond, the half arrow bond which you saw, and it shows how power transaction as a product of two variables takes place. One variable is effort and the other variable is flow. He also developed, he classified the role of the elements. He identified them. So you have junctions, you have elements, and you have connections. And then a very important aspect of physical systems, which is cause and effect. So he came out with this idea of cause and effect and how it should be represented. The idea of cause and effect is well known. It's also called causality. But representing it graphically it was a challenge, and it was beautifully represented using this technique. Now, cause and effect or causality is a very important characteristic of physical systems. It's a very important part of physical systems, and many times we just do not care about it. But sometimes the very existence of physical systems can be questioned based on this premise of cause and effect. There are a number of software available for bond graph for modeling. You have the most popular one today, commercially available, that is 20sim. You have Symbols Shakti, Symbols Vista. This software was developed by Professor Amalendu Mukherjee and his group at IIT Kharagpur, and it also was a very powerful and very popular software, and now it is much less visible, but while Professor Mukherjee was alive, certainly it was a very much used software in India. There are other software. You have CampG, you have Amesim, you have the NPort, the first software on bond graph, the NPort software. A number of software available for modeling of physical systems using bond graph, in which you can actually draw diagrams on bond graph on the screen, and then that can be translated into the pictorial. The pictorial grammar is then used to obtain the mathematical model. There is scope for providing causality and derivation of equations and a number of things which are needed for simulation thereafter. But we are not going to use this at NIT Jalandhar. We do not prefer to use this software, because after our experience of having used this software, we have always faced some problems or the other with these software, especially when their licenses get older, when the licenses have to be renewed, when newer versions, when the operating system gets outdated, the older software does not work efficiently. So there are a lot of such problems associated with the purchase of commercial software for the use of bond graph. And since we are in an academic institution where we'd like to have our students actively participating in the development of this technique, we decided to use MATLAB. So we do use MATLAB. Some of my students also use Scilab, and they do their coding using this. And it's very, very simple. It's a very algorithmic way in which this coding is done. And it's easy to program. All the control is with the modeler. We are not bound by the constraints that are offered by commercial software. All these commercial software have some constraints or the other. So the user has to actually fall in line with the constraints laid down by the software. Now, fortunately, we don't have this kind of constraint. So all the control is with the modeler. And it's easy to modify, append, etc. So if you want to make any changes to your model, you want to model some additional phenomena, it's very convenient and you can just modify the relevant code. Now, power transaction through a bond in bond graph, you have a very peculiar kind of bond, which is a harpoon arrow. Okay. And this is deliberately chosen as the channel for transacting power. That is because the developer, Professor Painter, wanted to differentiate between the signal arrow, which is a full arrow, and the power arrow, the power bond, which is a half arrow. Now, a signal arrow carries information of only one variable, but a power bond like this carries information of two variables. You have an effort variable, the effort at any time t, and a flow variable represented by f at t. So a product of these two variables at any time gives you power. Power is a scalar. In different energy domains, power has different meanings, connotations. So in the electrical domain, you have voltage and current. In the mechanical domain, we use force and velocity. We have pressure and volume flow rate. Product of these two is power. We have temperature and entropy flow rate. Product of this is power. We have torque and angular velocity. Product of this is power. So we have in different energy domains, we have different connotations for the variables of power, effort and flow. So the product of which is power. So you can see that using the same arrow, you can model in different energy domains. Now, Painter also presented the different elements. I'm not going into the details of this because I would rather like to give you a glimpse of the different aspects of bond graph and the applications rather than bog you down with the detailed nuts and bolts of this technique. So here you have two sources. You have a source of effort and a source of flow. You have elements, three elements. First one is the inertia element, the stiffness or the compliance element, and the dissipation element. You have junctions, 1 and 0 junctions, and you have transformer represented by TF and a gyrator which is represented by GY. So you can see that you have 9 elements. So you have one power arrow, one power bond. You have these 9 elements. And you have one very important aspect, which is causality. So in Causality is actually, it represents the cause and effect relationship between elements and subsystems as they interact with each other. So it's an input-output relationship essentially. So suppose you have two subsystems interacting with each other, that means exchanging power. So a channel of transaction of power is established. And as we saw, you have an effort variable and you have a flow variable. Now in physical systems, it's very important that if one subsystem provides the information of effort to the other subsystem has to provide the information about the other variable of power. So if effort is decided by A, flow has to be decided by B. Both effort and flow cannot be decided by the same subsystem. So A can decide either effort or flow. B can decide either flow or effort. In this particular representation, we have got A deciding effort and receiving flow, B receiving effort and deciding flow. Now, how do you represent this? You have one bond, but you have two variables. How do you represent the flow of information? So this is done using a causal stroke. So you have the end which is receiving flow shown over here and the end which is receiving effort shown over here. You can see. So these are signal arrows. And this one power arrow is doing the job of these two signal arrows. But how is the causality represented? It's represented using a simple stroke. The end which receives this stroke is the effort receiving end. So it automatically means that the other end receives flow. Here also, this end A is going to receive effort. So the causal stroke is going to come here. So this is how the causality of systems is represented in a very simple but elegant way graphically. And this concept of causality is extremely useful because using this concept, you can understand the physics, you can understand the interactions between interacting subsystems. You can use it also as a tool for computational causality. You can also use it for fault diagnosis and a number of other applications. So causality is actually a very powerful concept in bond graph and in physical systems. Now, there are developments in the bond graph theory. There are a number of developments which have taken place. There are multi-bond graph. Earlier, they used to be called vector bond graph also, but in order to avoid ambiguity, it was decided to call them as multi-bond graph. A lot of work has gone into the study of structural controllability and observability, which are concepts of the modern control theory. Several control strategies have been developed using bond graph. You have the concept of bicausality, which was also developed using bond graph. Concept of differential bond graph, use in fault diagnosis, a number of applications. So you can see that the bond graph is a powerful tool which can be used for modeling of physical system dynamics in multi-energy domains. Now, we have done some works at NIT Jalandhar, and using bond graph, and we applied it to robotics, because robotics is a very important aspect in our um, research at the mechatronics lab at NIT Jalandhar. Our work is mainly oriented towards rehabilitation. So we apply the concepts of robotics, the tools of bond graph and control theory, in order to develop ideas for prosthetic systems, for exoskeletal systems, for study of rehabilitation. So a number of these applications, all using bond graph, is what we will discuss in our presentation today. So at NIT Jalandhar, we have multi bond graph modeling of rigid body mechanics. We have developed a systematic theory. There are certain advantages to this. This has been done using bond graph. We have modeled a number of mechanisms and machines, robotic systems, crankshaft, connecting rod, piston cylinder mechanism, universal joint mechanism, quick return, pantograph, power hacksaw, epicyclic gear trains, differential gear mechanisms, the Cardan gear train mechanism, Fallow's differential mechanism, several mechanisms using the technique of bond graph. We have also applied it to more complicated aspects of soft contact dynamics, where we manipulate objects with our hands, with our fingers, but actually we are doing a lot of soft contact dynamics. Rigid objects interacting with soft material. The soft material is the pulp of our fingers, and that provides us with a lot of versatility, with a lot of capability in order to manipulate objects. We have also developed a lot of things in biomechanics, understanding various aspects of biomechanics, especially in the development of hand prosthetic systems and extensor and flexor mechanisms of the hand, the Winslow's tendon network. We are also working on understanding the carpal mechanics, the wrist mechanics. There are a number of bones at the wrist, and how the phenomenon of wrapping of ligaments and tendons is taken care of in this wrist. So that's also, everything is done using bond graph. We also apply bond graph to control systems. We have developed force and trajectory control of tendons, and we do all our coding using MATLAB and Scilab. And a lot of our work goes into our teaching and learning process. So the students at the mechatronics lab at NIT Jalandhar are familiar with this while they intern here, while they work on their projects. They do a lot of learning, they do a lot of application, they try a lot of hands-on work in their projects, and a lot of meaningful project work is done. We also develop experimental setups for academics and research. A number of low-cost, meaningful, innovative experimental setups have been developed. So these are some of the things at NIT Jalandhar. Before I go into the rigid body mechanics, I'll just give you a brief idea of what we have done, just to show you what I teach sometimes, the very basics. Here you have a two-link planar mechanism, a planar robotic mechanism, you may call it. One end is hinged here to the ground, and you have you have two joints which are revolute in nature, and you have the tip over here. Now you would like the tip to move along a straight line, let us say. So you would like to model this system. So we can model the dynamics of each of these links. So here you have the translational dynamics, and here you have the rotational dynamics. You provide the torque at the joints, respective joints. But here, if you want this mechanism, if you want the tip to follow a particular path, you would actually need the information of the joint angles, or you would need information in the joint space if you have information of the tip in the Cartesian space. So if you drag this tip along this, the mechanism is going to generate motion at its joints, and you will be able to sense what these angles are going to be. So it's actually, in a sense, you are obtaining the inverse kinematics of this mechanism through the dynamics itself. All that you're doing is making the tip follow a particular trajectory. The reverse is an easier process. If you know the joint angles, you can obtain the path of the tip. That is forward kinematics. For this inverse kinematics, you can bypass this inverse kinematics in this way. So here I'm showing you a small animation when you animate this model which has been done. So you can actually, this is a MATLAB animation of this. So here the dynamics has been taken into account, but since only the intermediate frames have been shown, it may appear to be a bit coarse. So this is for a planar two-link mechanism. Let's see a 3D mechanism here. So here we would like that the tip of this revolute joint manipulator. So here you have the waist joint, here you have the shoulder joint, and here the elbow joint. And you would like, so here you have three bodies, and the translational and rotational dynamics of each of these is shown here. You would like that the tip should follow a particular path, a circular path, which is shown here. So when you make the tip follow this particular path, automatically you obtain the joint histories, the trajectories, joint trajectories that are needed to obtain this path. So you're actually again obtaining the inverse kinematics indirectly through the dynamics. So this is the application of bond graph, multi-bond graph, to this simple application, and this is what I teach in my course on robotics, on the mechanics and control of robotics. We have also applied the idea of bond graph to a number of mechanisms. One of them is your Cardan gear mechanism, and the mechanism shown here is actually meant to draw straight lines, but the mechanism has only geared gearings, spur gearings. It's a mechanism made of spur gearing only. So you can see that it performs its functional task. Now coming back to the development, coming back to the topics, we deal with the modeling of rigid body mechanics using bond graph. So here you have the dynamics of links and joints. We have to model these using bond graph. We are dealing with the mechanisms used in robotics, and they are usually made of rigid links. And these links are actually connected at joints so as to obtain useful configurations. We have the revolute joint. These are the most common joints: revolute joint, the prismatic, and the spherical joints. These are the most common joints. Uh, a brief review of this rigid body mechanics is essential. I'm sure you must have done it at the undergraduate level or at the postgraduate level, but I'm just going to just roughly skim through it, just to give you an idea of how it is represented using bond graph. So you can begin with the idea of the system of particles, the dynamics of a system of particles, and then constrain the system of particles to obtain a rigid body. So in this system of particles, you have a number of particles which can move anywhere, and each one has a mass. It's treated as a mass point. And you have the center of mass, which has a particular definition, mathematical definition. So here you have force represented on the ith particle, represented here. You have the force represented on the jth particle. And between these particles also you may have a force. We assume that this force, just like gravity, may be directed along the line which is joining these particles. So these are the internal forces. This is the force on the particle J due to the particle I, and this is the force on the particle I due to the particle J. So it is equal and opposite. Now this is a particular category of forces. It could be electrostatic forces, it could be gravitational forces, but not magnetic forces. Now the center of mass. So in the definition of the center of mass, we define it mathematically like this. Okay, so if you take the moment, mass moments about the center of mass, it works out to 0. You have conventions for scalar and multi-bonds, and the convention that we will follow is we'll have a scalar bond representing effort and flow. The product of these two variables is power. If we have several such scalar bonds, say E1, F1, E2, F2, and so on up to En, Fn, we can represent this as just one single multi-bond like this. Here we have n scalar bonds, so we can represent it using the cardinality n. So we can represent all these efforts as effort vector, E vector, and all these forces as a flow vector. Now, what is power in the case of multi-bonds? Power is going to be the sum of all these powers. So E1 F1 plus E2 F2 and so on. So power is going to be this summation. So E transpose F, which is F transpose E. I'll just pause here for 2 minutes. Please give me 2 minutes. I'll just join you shortly. Please hold on.